Hello, students. Welcome to our presentation on substitution reactions in organic chemistry. We'll explore nucleophilic, electrophilic, and free radical substitution reactions, focusing on their mechanisms, kinetics, stereochemistry, and factors influencing reaction rates. Nucleophilic substitution reactions involve a nucleophile replacing a leaving group in a molecule. Here, we see examples of alkyl groups reacting with nucleophiles to form new compounds. Nucleophilic substitutions are categorized into SN1 and SN2 types. We'll discuss their definitions, mechanisms, kinetics, stereochemistry, and factors influencing their reaction rates. Let's first discuss about SN2 reactions. In SN2, a nucleophile attacks the substrate, leading to a bimolecular substitution. Examples include reactions with alcohols, ethers, thiols, and more. The mechanism of SN2 involves the nucleophile and alkyl halide forming a pentacoordinate transition state, which is the slow, rate-determining step. Kinetics studies the rates of reactions. For SN2, the rate depends on the concentration of both the alkyl halide and the nucleophile, following the rate law, rate equal car XO. SN2 reactions involve a planar transition state and result in the inversion of the chiral center, known as Walden inversion. Further, SN1 reactions involve a unimolecular nucleophilic substitution. An example is the solvolysis of tert-butyl bromide to form tertiary butyl alcohol. In SN1 mechanisms, the leaving group dissociates to form a carbocation, which then reacts with a nucleophile to complete the reaction. The kinetics of SN1 reactions are first order, depending only on the concentration of the substrate, with the rate law, rate equals Krx. SN1 stereochemistry can lead to partial racemization and inversion due to the planar nature of the carbocation intermediate. In reality, SN1 reactions can form ion pairs, leading to a mixture of inversion and retention products. Factors influencing reaction rates include the substituent, nucleophile, leaving group, and solvent effects. For SN1, electronic factors govern the stability of carbocation intermediates. For SN2 reactions, steric factors govern the ease of nucleophile approach. The reaction is fastest with unhindered halides. Further, nucleophiles are neutral or negatively charged Lewis bases. Their reactivity depends on their charge and position in the periodic table. Good leaving groups are stable anions that can delocalize charge. Weak bases make excellent leaving groups. Solvent effects play a crucial role. Protic solvents favor SN1 reactions, while aprotic solvents favor SN2 reactions. Solvents that donate hydrogen bonds slow SN2 reactions. Polar aprotic solvents form weaker interactions, permitting faster reactions. Electrophilic substitution involves an electrophile displacing a group in a compound. This can be aromatic or aliphatic substitution. Electrophilic substitution can be unimolecular, bimolecular, or internal, depending on how the electrophile attacks and assists in the removal of the leaving group. Nitrosation involves the reaction of secondary amines and mono-N substituted amides with nitrous acid, while nucleophiles like Cl, SCN, and thiourea catalyze the reaction. In aliphatic diazonium coupling, compounds with active hydrogen couple with diazonium salts in the presence of a base, following an SE1 mechanism. Electrophilic aromatic substitution replaces a hydrogen atom on the aromatic ring with an electrophile. The mechanism involves the formation of an rhenium ion, with the proton being removed by any of the bases. Students, please note that various reactions such as halogenation, nitration, sulfonation, Friedel-Crafts alkylation, and acylation can occur on an aromatic ring, each with specific reagents and conditions. Substituent groups on a benzene ring affect electrophilic aromatic substitution reactions by influencing reactivity and orientation, directing the reaction to ortho, para, or meta positions. The reactivity and orientation of substituent groups on a benzene ring determine the position of electrophilic aromatic substitution, with some groups directing to ortho-para positions and others to meta positions. When multiple groups are present on a benzene ring, the more activating group directs the next substitution, with minimal substitution between meta-directing groups. Alkanes undergo free radical substitution reactions with halogens in the presence of heat or light, leading to a mixture of halogenated compounds. Bromine is less reactive but more selective than chlorine. The mechanism of free radical substitution involves 3 steps: initiation, propagation, and termination, with each step producing and reacting free radicals. Termination in free radical substitution involves the reaction of free radicals to produce a stable molecule, often requiring constant irradiation to replace quenched radicals. Radical halogenation at an allylic carbon often results in a mixture of products due to resonance stabilization, as seen in the example of 3-bromo-1-butene and 1-bromo-2-butene. The reactivity of CH bonds in radical halogenation depends on bond strength and radical stability, with weaker CH bonds being more readily removed. The planar structure of alkyl radicals allows for attack from both faces, leading to the formation of racemic mixtures in stereochemistry. Electrophilic addition reactions occur in unsaturated hydrocarbons with double or triple bonds, where p electrons react with electron-deficient compounds to form addition products. Electrophilic addition reactions are second-order and exothermic, involving the formation of a carbocation intermediate and resulting in 2 stronger bonds. Electrophilic addition can occur via syn or anti-addition, with carbocations being planar and allowing attack from both sides. Bromination of alkenes involves electrophilic addition, with the formation of a cyclic bromonium ion and subsequent attack by a bromide nucleophile. Students, now let's discuss about Markovnikov's rule. It states that in the addition of an unsymmetrical reagent to a double bond, the positive portion attaches to the carbon with more hydrogen atoms, forming the more stable carbocation. Addition reactions are regioselective, favoring the formation of the more stable carbocation, as seen in the examples of secondary and tertiary carbocations. In the presence of peroxides, the addition of HBr to alkenes follows a free radical mechanism, leading to the formation of the anti-Markovnikov product. Radical addition in the presence of peroxides leads to the formation of the more stable radical, resulting in the anti-Markovnikov product. Carbocation rearrangement is a key concept in organic chemistry, where a carbocation shifts to a more stable position. This slide illustrates the formation of a favorable tertiary carbocation and the subsequent reactions involving 2-phenylbut-1-N and 3-phenylprop-1-ene. Alkenes can undergo various addition reactions. Here, we see the addition of halogens in water forming halohydrins, under basic conditions forming epoxides, and the anti-Markovnikov addition of water following hydroboration. Alkynes also participate in addition reactions, particularly the addition of halides. This slide details the formation of primary and secondary vinyl cations and the stabilization mechanisms involved. Elimination reactions often compete with nucleophilic substitution reactions. The slide explains how nucleophiles can attack electrophilic sites to give substitution products or act as bases to give elimination products. Elimination reactions typically produce a new pi bond, but sometimes a new sigma bond is formed. The slide also lists common leaving groups necessary for these reactions. Elimination reactions can be unimolecular, E1, or bimolecular, E2. This slide shows the mechanisms and conditions for both types of reactions. The E1 mechanism involves 2 steps: breaking the Ci bond to form a carbocation, followed by the cleavage of a CH bond to form a pi bond. Kinetics of the E1 reaction are first order, with the rate depending on the concentration of the alkyl halide. More substituted halides react faster, and polar protic solvents favor the E1 mechanism. According to Zaitsev's rule, the major product in elimination reactions is the more substituted alkene. This slide explains the removal of hydrogen from the beta carbon bonded to the fewest hydrogens. Hofmann elimination produces the less substituted alkene, especially when the base is bulky or the leaving group is poor. This slide compares different scenarios leading to Hofmann products. Comparing Hofmann and Zaitsev products, bulky bases increase the proportion of the less substituted alkene. This slide highlights the steric accessibility of hydrogens on beta carbons. In E1 reactions, carbocation intermediates can rearrange before losing a proton. This slide compares substitution and elimination products in SN1 and E1 reactions. The E2 mechanism is second order, with the rate depending on both the alkyl halide and the base. Strong bases and polar aprotic solvents favor E2 reactions. Stereochemistry plays a crucial role in E2 reactions. The leaving group and hydrogen can be syn or anti to each other, with anti-elimination being more favorable. SN2 reactions often compete with E2 reactions for substrates that are good for SN2. Strong bases or non-nucleophilic bases promote E2 over SN2. Thank you for watching this presentation on organic chemistry reactions. We hope you found it informative and engaging.